Okay, well, I hope this is recorded. It was a minute ago. Uh, so what we want to do is give you a pretty good picture of what to expect on the exam. Okay? In the exam, I intend, if this whole thing doesn't delay things too much, I intend to get it in the test this afternoon. It'll be late this afternoon, most likely. I know what I want to put on it, I just haven't written it yet, but that will take me 3 minutes. So I shouldn't have any problem getting it in. I'll also send out some sample problems that might be as late as tomorrow. Depends. All the disruptions and stuff. Clear. I hope I don't have to repaint this board because it's hard to get paint to go on smooth. Other than that, it's great stuff. Okay, so we'll first talk about the new stuff that's going to be on the test, and then stuff from previous chapters that might also appear, stuff that you studied for the midterm. But the problems aren't going to be quite as predictable as they were in the midterm. Just be sure you've got that material now. I sent everybody a PDF with comments. Did everybody get that? Were you able to read the comments? Okay. Okay, good. Okay, so what we're doing from the current chapter, we're not going to do the rational functions, although I will put a rational functions problem on the test as an optional problem. I've said that before, but just want to reinforce it. Okay, so basically what we have here is power functions. Quadratic functions, polynomials, and rational functions. Okay, so power functions. The form y equals x to the p, but the functions that we're going to use in this chapter, we're going to have integer powers, so I'm going to use n instead of p. If I use n, that kind of implicitly talks about just numbers and then counting numbers, or integers, because n can be negative. Okay, the cubic function, and I'm just going to do this on the right half of our standard rectangle. It's not 4 by 4 anymore. It's 2 to the third by 4, which is 8 by 4. So that this line would be the x equals 2 line, and this line would be the y equals 8 line. Of course, y equals 0 down here. The algorithm is Okay, remember that for the squaring function, we divide this thing in half. One time, if it was a squaring function, then y would be 4 up here. So you go from 4 down to 2, down to 1, down to 1/2, down to 1/4. And then we do an extra line here because our rule then is start here, move over 1, down 1, over 1, over 1, down 2, over 1, down 2, over 1, down 2. If we don't have that dotted line in there, we can't go down 2 from this last point. Okay? And then from here we go over 1, up 2, over 1, up 2, over 1, up 2, right? So let's just think about what we do in this quadrant. Over 1, up 2, over 1, up 2, over 1, up 2. For the cubing function, it's got to be over 1, up 3. Okay? Which means we're going to need some more halving lines down below this dotted line that's already hard to draw. So we can't really do that. So what we do is we start here. We're going to go 1 to the left and down 3 instead of 1 to the right and down 2 like for the squaring function. For the cubing function, we don't want to go over 1, down 3 because the cubing function doesn't include this point. Okay? So we've got y equals 8. We go over 1, down 3, which is at this point. Of course, what's this? Well, this is y equals 4. Here's y equals 2. Here's y equals 1. Now this is the line x equals 1. And 1 cubed is 1, right? So for n equals 3, we get y equals n x cubed. Okay. Now we come over 1, now we've got to go down 3 more lines. We've only got 2 lines to go down. So we're going to have another one down here that you almost can't draw. So this thing gets down here really close to the x-axis. And then you get over 1 line, down 3 more. You can't draw those 3 lines. But you know you're going to end up at the red dot, the origin. Because x 0 cubed is 0. So now you get this graph. Of course, I had this point, that's where we started. This graph stays really flat, and then it goes up really fast. Much flatter than the squaring function. If we wanted to compare this with the squaring function, we could do it. We've got a grid here. But the squaring function would go over to here. Sorry, go from here, up here, and up here. So it would be kind of like this. And it's not so flat down here. It would stay above the cubes function. What I'm trying to do is just give you a picture of the way these functions develop, okay? And then for the cubing function, you would reflect all these points through the origin, which means there would be a rectangle down here, and the graph would come down very flat and very fast like so. If you went to the x to the 5th function, you'd have to go over 1, down 5. But the grid would be 2 to the 5th. I mean, the height of the rectangle would be 2 to the 5th, which would be 32. So instead of y equals 8, you'd have 32 here. So 1 would be down really close to the x-axis. And 1 would be found by going over 1 and down 5 lines. And then you go over 1 here and down 5 more, and then over 1 and down 5 more to get to this one. Most of those lines are invisible, meaning it gets really flat, really fast. But once it crosses x equals 1 point, it gets really steep. Does that make sense? Okay. Well, x to the 4th is similar. Of course, x to the 4th, you can do it just in this one square. So those are the shapes, and that's kind of the geometric connection to the shapes in the way we learn to construct them. I'm not going to ask you to construct these because you can't even draw them, but you got to understand how the power functions behave. Okay. The main use of power functions is going to be that when you have a polynomial function, the leading term is a power function, right? If it's x cubed plus x squared and so forth, that's going to act like this in the long run. We've seen that already, but you want to keep that in mind. As I said before, you have the leading power function with wiggles. Okay? And if you have rational functions, well, you get a power function with wiggles and asymptotes. And we won't talk too much about that today, because that's not going to be required on the test. Incidentally, listed rational functions in parentheses, indicating it's going to be an optional topic. Okay, quadratic functions. Well, you know, really, there's stretched and shifted scoring functions. Their functions will write g of x equals a times f of x minus h plus k for f of x equals x squared. Well, if f of x equals x squared, then this is a times x minus h squared plus k. This is a vertex form. And what this means is you start with your toolkit squaring function. Okay, no construction lines and stuff. Okay, but there's the shape of the function. And the vertex is at the origin at the red dot. Stretch. And maybe reflect. You turn it upside down. And you get a function that you can still construct the same way. You can draw your construction lines in any rectangle. The red dot is still going to be at the origin. This line is still y equals 0. It just looks skinnier. Okay? It gets taller, it doesn't get wider. stretch factor is A. Now A also could be negative, which means that you'd also have a reflection. If A is negative, this thing would be upside down. But the red dot would still be at the origin. Okay, so this line was y equals 4. This line was y equals 0. We know what the x lines are. I'm not going to take the time to label them, but you would need to. Okay. If you're vertically stretching by a factor of 2, then A would be 2, right? A was 2, you'd vertically stretch it twice as high. And then, instead of y equals 4, this would become y equals 8. Okay? Well, it looks like this is about double. Okay? So maybe here A is 2. And this is 8 up here. Whatever A is, y coordinates of all these construction lines that you sketch are going to be multiplied by that number. So like the y equals 2 line here would correspond to the line halfway between here and here. This would be y equals 2a and so forth. And then you shift so that the origin becomes the point HK, because you shift horizontally H units and vertically K units. You'd be very familiar with the transformations and how they work, and understand quadratic functions in terms of the transformations, because the vertex form is particularly simple. It tells you basically how to graph it. It tells you where the vertex is going to be and what the shape is going to be. Now, general form. G of x equals ax squared plus bx plus c. Whatever these numbers are, you can square this thing, multiply through by a, and add k, put all your terms together, it's going to look like this. A is going to be the same as it is here, because when you square x minus h, x will end up multiplying x to give you an x squared, and it's going to be multiplied by a, so you're going to have an ax squared. Then you're going to have a bunch of other stuff depending what the numbers are. But you'll end up with something in front of x, and you'll end up with some number on the end. Okay? Got the quadratic formula from very likely know pretty well by now. And you've got the x coordinate of the vertex, negative b over 2a. Now, these are zeros. Zeros could be complex. You've got a negative under the radical. Okay? Or the zeros could be repeated. You could have 0 under the radical so that b plus 0 and b minus 0 are the same. That would be a repeated root. That would give you a multiplicity of 2. Or, what you got under the radical is positive. So, the plus gives you one result, the minus gives you a different result. So, could have two real zeros, so you get two x-intercepts. With the axis of symmetry halfway between them, because this thing is symmetric. Now, what's the axis of symmetry? Well, here's your axis of symmetry here. Axis of symmetry is here. When you get this into its final position, this red dot could be below the x-axis, in which case the graph would have to go through the x-axis twice. Okay? And that would correspond to having a positive number under this radical. Or the red dot could be sitting on the x-axis as it is right here. Okay? In which case you have 0 under the radical, and you have a root of multiplicity 2. Or it could be totally above the x-axis with only complex zeros. This corresponds to negative. Okay? So could have two real zeros under it too. Graph here, red dot, which we can also call the vertex of this function. The x-axis, got a 0 here. Well, the two zeros give you two x-intercepts. A 0 is when this thing equals 0. Okay, it's a solution of this equation equals 0. If you have real solutions, you get x-intercepts. If you have complex solutions, you don't get x-intercepts. Okay. We want to write a square root of that. So this is a case, I just read, and you might not be able to read it because of the smudges. It says b squared minus 4ac is positive. Okay? It's going to look like this, or maybe it's upside down with the red dot above the x-axis. So I can draw that possibility too. These two pictures correspond to this. Or you could have one repeated 0. That looks like this. It looks like this. There's some unusual red dot. Usual parabola, or parabola could be upside down. But it's going to hit the x-axis just at that one point. That's what it's going to look like, the repeated 0. And of course, this is the case of b squared minus 4ac equals 0. Or two complex conjugate zeros, in which case thing is going to be like this. Or what is this? Let's pick quadratic functions. Everything I did over there was visible. Wasn't when I started. Okay. If it's in vertex form, Q of x equals 0 means, well, the vertex form equals 0, so that a times x minus h squared equals negative k, meaning s minus h squared equals negative k over a, meaning x minus h equals plus or minus the square root of negative k over a, which means x equals h plus or minus the square root of negative k over a. Nothing numbers there, those are the steps you go through to solve. You add this number to both sides, then you divide both sides by a, you get this. Then, if something squared equals this, then something that's squared equals plus or minus the square root of that thing. Now, the square root of that thing, you got a negative k over a, right? Does that make this a negative number? Well, no. If k is a negative number, then negative k is a positive number, right? Or if k is a positive number and a is a negative number, this number is going to be positive. And that corresponds to the quadratic formula. But the main reason I mention that is you might well see a vertex form, and I ask you to solve the vertex form equals 0. So, fairly simple. We've been over it. You just got to remember that the one tricky thing is x minus h squared equals something, and x minus h is plus or minus the square root of that something. This could be positive or negative, so you could have, or it could be 0. Okay? If this thing is 0, then you got this. If it's negative, you got this. If it's positive, you got this. So you might want to think about that. Vertex is at x equals negative b over 2a, which is the axis of symmetry. Get the y coordinate. Whatever negative b over 2a is, you plug that into the function for x, and you get the x coordinate. Okay? So what I expect you to be able to do is use these ideas, construct one by transformations. If I give you the shifts and stretches, you should be able to figure out what the form is. Okay? Because if you've got horizontal vertical shift and a vertical stretch, it's always the form of the function, where f of x is the toolkit function, or whatever function you're stretching and shifting. In this case, for the toolkit function, do this, you get one of these. And do this, get your numbers for A, H, and K, expand it, you get this form. You find the vertex, you find the x coordinates, and of course you can always find the y-intercept. That's the easiest thing to do. So, I haven't mentioned it, but everybody seems to be doing that. Okay. Well, that's pretty much what you need to know about quadratic functions. Polynomials. What I'm really looking for is you understand a polynomial if you know its factor form. And sometimes I want you to be able to find its factor form, just for like a cubic polynomial. And we'll talk about that. Okay, so for polynomials, P of x being a polynomial is the product of linear and irreducible quadratic factors. But it doesn't always look that way. Okay? Looks like this. Don't know if I've ever written that form out. It's just a bunch of powers of x. If n is the highest power, then there's your leading term. It's got some number in front of it, right? We'll call that number a sub n. Then the next power down, n is a power b n minus 1, one less than n. There'd be some number in front of it. We just call that a sub n minus 1, just for compact notation. And you understand that this is, for example, here. The highest power is your leading term. In this case, the leading term would be 5x to the fourth. Like 5x to the fourth, which is just like x to the fourth. So the long run behavior looks kind of like this. with wiggles. And you'll see me talk about that. Just reminding you, long run behavior is this, and then wiggles. It might wiggle through the x-axis, it might wiggle above the x-axis, it might wiggle below the x-axis, it might not even look like it wiggles. But it can have wiggles. And if it's an x to the fourth, it can have at least, can have up to 3 wiggles. Zeros come from linear factors. If the polynomial is a continued factor. Reducible quadratic factors don't have zeros. That is, your discriminant b squared minus 4ac is less than 0, so you don't get real zeros. Okay? They have zero. As a mistake, but they don't have real zeros. So they don't yield x-intercepts. Okay? Graph. Locate the zeros and note the multiplicity. Find the y-intercept. Sketch a smooth curve. Consistent with the long-run power function. Passing through or touching all the intercepts. Might be a little hard to read that. I'm sorry about that. Okay. What does that mean? Well, you got to go through the y-intercept because it's a function. You can't just touch the y-intercept and turn around because then you failed the vertical line test. But if the zero has an even number multiplicity, you're going to hit it like a corresponding power function. It's got multiplicity 0, it's going to come down, and it's going to be like a parabola, just real, in the immediate vicinity of the 0, right? If the 0 has multiplicity 3, then a real 0 has multiplicity 3. Then you're going to come down like this. And maybe it comes down from the left and smooths out the reflection of this. And maybe it comes up and goes through just like this does. There's going to be your 0. And as you get away from here, it's going to get distorted. It's going to turn a different way or something. But in the immediate vicinity, it's like this. So, well, I want to do an example. Well, I'll do a simple example. That'll be more complex. Example. It's x minus 4 times x plus 2 times x squared plus 2x plus 10. I got the word or between these. You have to know that to set this equal to 0, this has got to be 0, or this has got to be 0, or this has got to be 0. You only get 0 from this set of factors, a set of quantities that are multiplied if one of them is 0, at least one of them is 0. So you get x equals 4, x equals negative 2, and you solve those equations. These are easy to solve. You can immediately see what the solutions are. This is quadratic. It's irreducible because if you set it equal to 0, you get a negative under the radical. So it's complex, not real. It doesn't give you 0. It does give you, well, it doesn't give you an x-intercept. These do. So what you have, okay, now, it's degree 4, then it's like x to the 4th in the long run. So that means x to the 4th has to go up on this side and up on this side because the graph of x to the 4th looks like this. It's going up on this side, it's going up on this side, and it's getting steeper and steeper, and it ain't coming back. Okay? So there it is. And then you have your 0 at negative 2. At x equals 4. Didn't do that very well. And of course, you have your y-intercept, which is at negative 4 times 2, which is negative 8 times 10. That's on the line y equals negative 80. So the graph is going to come down through here. Try to go down a little lower than this before it turns around. It's going to come back up. Kind of looks like a parabola, but it's going to get much steeper. and probably flatter down here. Okay. Now we've graphed a lot of these. There's your context. There's more. If P of, we'll call it R, equals 0, and X minus R is a factor of P of X. Then this division ends up with no remainder. Now, P of X is just whatever the polynomial is. You write it out. Okay? And you do the long division if you want really good with that. And when you do it, if you do it right, if R really is a 0 or of the polynomial, the division is going to come out even. You're not going to have any remainder. And P of X is X minus R times Q of X. For Q of X, I have 1 degree less than P of X. Example. Okay, let me be careful. Let's check that. I say it's 0 for X equals 2. If it isn't, I'm going to fix it. If X is 2, that's going to be 8. And this is going to be 8. That's 16. 6 times 2 is 12. So you've got minus 12 and minus 4, which is minus 16, right? Leave that up to 16, leave that up to minus 16. It's 0 for X equals 2. So this shouldn't have a remainder. if it's so. Of course, you write out P of x when you do the long division. Divide x into x cubed, you get x squared, giving you x cubed minus 2x squared. But that's going to be like a plus, and that's going to be like a plus. And you're going to have 4x squared minus 6x, which will give you then 4x, which then multiplied by x minus 2 gives you 4x squared minus 8x. This is subtracted, that's added. This gives you 2x minus 4. X goes into 2x 2 times, and it gives you 2x minus 4, no remainder. Okay. Is this polynomial, is it quadratic irreducible? Well, if you check the discriminant, b squared minus 4ac is plus 8. Okay? So this can be solved. You can check me on the square root of 8 thing. But you find that this is 0 when x is negative 2 plus or minus the square root of 2. If you want to write it in factor form, this makes it 0, so you're going to have x plus this, right? And what? How is this 0? This is 0 if x equals the negative of this. Should be x minus. And I didn't do that, that was pretty good. Okay. If x equals negative square root of 2 plus negative 2 plus the square root of 2, then this is going to be 0, so the whole thing's going to be 0. If x equals negative 2 minus the square root of 2, then this is going to be 0, the whole thing's going to be 0. So there are your zeros. You can approximate these zeros. That's going to be like negative 3.4. And this one's going to be like, no, that's going to be like negative 0.6. That's going to be like negative 3.4. Anyhow, there you have it. So now you can graph the thing. So I could well give you a polynomial of degree 3. That wouldn't go beyond that. I just want to see if you can do this. And I might or might not tell you what the 0 is. I might say, well, there's a 0 someplace between negative 3 and plus 3. Plug in and check it out. Okay? I might narrow it down a little more. Okay, maybe it's between 1 and 3. That's not that. Okay? Again, I might well give you, I might well tell you what the 0 is, but I might well make you work for it a little bit. Now there's a rational roots theorem. It's kind of an important thing. Are we still recording? Apparently we are, but apparently we've gone out of focus. How could that happen? This thing doesn't have, maybe it does have an autofocus. You can pretty much read it, but it's not as clear and sharp as it should be. So there's an anomaly in this camera. Let me take a chance. Oh, that's not anything to make anybody happy. Why in the world isn't it focused? I think it's still basically readable, but it's going to be okay. Okay, again, I might well give you that. I said the rational roots theorem, and we're not going to use that. Okay, it's not very important except theoretically, because in the real world, any polynomial you get has zero chance of having rational roots. Okay, at least in most applications. You generate a random polynomial. Okay, well that's kind of, does that give you a pretty good idea what I'm likely to ask on the chapter 4? Okay. For previous chapters, I'm just going to list topics because I'm not sure you're going to be able to read what I write anyway. Maybe it's my eyes. Where are my glasses? But you don't look blurry. Do I look blurry? I mean, sometimes I do, I think. Now with my glasses on, I can see, yep, it really is a little bit blurry. I can read it. You probably can too. And we'll see if we can do something about that aspect of this camera. Okay? It was beautifully clear when we started. I don't know what's confused me. Okay, well, anyhow, big thing from earlier chapters of transformations. And you remember the first and last problems on your test, right? The first one where you construct a thing and move it and all that stuff. Okay, and you want to review that. You want to be sure you can do that because there's going to be one of those on there. And the last problem where you're applying a linear function. The one where you could get 20 points if you got it right, 10 points, and 20 points if it helped you, 10 points otherwise. You really want to review. You want to review everything that was on the test, but everything that was on the entire problem. Okay. Now the problems won't be exactly the same as they were, but okay, you got transformations. I'm not going to say any more about that because I think y'all are pretty good with that. But make sure. Composite functions. You can expect me to probably ask you to tell me what two functions make the composite of a given function, as I did on the test. It won't be the same two functions. Okay? It'll be different functions, but it'll be something that's fairly obvious if you know how to do that. So that's something you want to review. How to decompose a composite. That is, find the parts of it. Okay? Rate of change, that's something that people do pretty well on the test. Okay? you got to be able to do a rate of change at a given interval. You got to know what that bracket thing means. It's not the coordinates of a point, it's an interval. OpenMath uses that same notation. You should be used to that notation. So you should understand interval notation with brackets and parentheses. Just because two numbers are in parentheses doesn't mean they're the coordinates of a point. Okay? We'll be able to solve for the intersection of two straight lines. You have to do that in homework. You do it by graphing, substitution, but elimination is what I'm really probably going to ask for. And graphing, okay? You might say here are two equations to two lines in one form or another. 3x plus 4y equals 7 is the equation of the line. Y equals negative 5x plus 4 is the equation of the line. Put it in any form. In whatever form you have it, you should be able to graph it. Find the intersection point. Then use elimination to find the intersection point more accurately. The graph should be consistent, but it might not be exactly the same as the accurate solution, okay? But it should be reasonably close. We've done a lot of that. Okay, inverse functions. Inverse functions. Just swap x and y on the table or the graph or in the equation of the function. And in the last case, solve for y. And verify f inverse of f of x equals f of f inverse of x equals x. All that's there. You did it in OpenMath. You got explanations in OpenMath. I've done it in class. Okay. And one thing I didn't penalize very heavily, if at all, on the test, first test, was this verification step. Still didn't do well on that part. I said, okay, well, I have to do it in the midterm, so you can guarantee it's going to be in the midterm. I want to see that verification step. Let's see if there's anything else. I've got another minute. I'm just trying to think back through the chapters. Now, when I say solve for the intersection of two straight lines by graphing, you got to be able to graph the lines. Okay? I could give you the lines as here's 2 points in the line. Find the equation. Here's 2 points in another line. Find the equation. Right? And now tell me where those two lines should cross. So you should be able to write out the equations of the lines and solve them. Over the next couple of days, I'll give you more examples and stuff. With all the confusion, the midterm just kind of piled up on us. I'm trying to do this for all my classes. So it's going to come out. First thing I'm going to do is get a test in this testing center. Then I'll send out a few sample problems. maybe some words of explanation in addition to what I've done here, if I've forgotten something. Okay? Again, nobody in here today, and most of the people have been attending classes. I don't see anybody who's in serious danger of failing the course if they continue to work. Okay? Everybody, well, but the drop date is next Wednesday. So, if you're uncertain, and this is probably more to people who aren't here today than are, although some of the people who aren't here today are doing quite well. If you're on the fence, you don't know whether you should drop or not, okay? Again, I'm not talking so much as a choir here. Because there are a couple of people who could be in that situation. And of course, if you goof off in this midterm, you could be too. Okay, so don't do that. And you haven't shown a tendency to do that, so I don't think you will. But I can do an administrative drop with the possibility of reinstating over the next week or two, okay? And anybody that looks like they're in questionable shape, I might just do that, okay? Because all you have to do is ask and I'll put you back in, okay? And it gives you a couple of weeks to get your feet on the ground. We're through the hard part of the course, believe it or not. Okay, the hardest stuff is probably rational functions. For most people, it depends. So the exponential functions, a couple of rules you got to know. You got to be able to do the inverse of an exponential function and apply it. But it's not too bad. And sometimes the making stuff, you know, the elimination stuff, gives people trouble because they have arithmetic skills aren't totally up to them. Okay? It's not that bad. Okay, well, anyhow, that's where we are. So you can take the test anytime next week, but you won't get the feedback on how you're doing really in the course by midterm by the drop date if you don't take the test by next Tuesday. Okay? If you take it by next Tuesday, then I'll have time on Wednesday to get through it and let you know. But Wednesday midnight, your opportunity to drop is gone. Okay? Again, talking more other people that might be listening to this and whatever, and to the people I see here. Okay, very good. Let me know if you have any questions. Let me see if this thing will. Allow me to stop it.